Hi, everybody. It's Prep with Zep, Joey, back to you with some digital systems. Uh, as I say with every video, if I get something wrong, I'm a student. Uh, Please do not blame me. And it is currently 9 p.m. We might go pretty long, so I might increasingly get tired. I will also be taking breaks probably in between, and I'll try to stop the video and record another one so you guys won't have to wait through them. Yeah, and nonetheless, this is ITI 1100. My friend sent me the PowerPoint presentations, so I'm just going to be going through them, pinpointing what is the most important concepts and trying to give more detail than the professor has previously told you. So I'm guessing he introduced you to different numbering systems, as you can see on the screen: decimal, octal, hexadecimal, and binary. Uh, Pretty much the key thing to do is conversion, which you'll probably detail in the further slides. This is week 1, so I'm just gonna take a quick look. Yeah, he talks about representation of numbers, how you would convert from one to the other. I'm gonna give you like a quick 4 minute like rules of conversion and how you should do so. And try to keep this as least complicated as possible. So this is pointless stuff. This is, let me get to this numbering slide. Okay, right here. So we have normal decimal, uh, which is basically counting from 1 to 3 onwards to infinity and backwards. This is how we usually count numbers. And basically, in digital systems, we try to shorten this up because holding this much memory is really expensive. So the next system that we use is Octal. Octal is basically, we represent every number in terms of like 3 bits. So you know that we have 3 bits, which could be 111. This is equal to 8. And that's like the octal representation. So let's say you have 0. Well, 0 is actually represented in the system as 000. Then you have 1 in octal, which is actually represented as 001. Okay, and then you can ask yourself, what is the max representation? Actually, this is 1 plus 2 plus 4, which is 7, not 8. My bad. But you can ask yourself, okay, if you are only allowed 3 bits, what's the max number that you can represent in an octal counting? Well, that is 7, because if you have 1, 1, 1, well, that adds up to 7, and that's it. If you wanted to go to 8, you would have to add another bit. So 8 would be 1, 0, 0, 0. But in the system, we unfortunately do not have that last bit, so we are stuck at 7. So octal is from 0 to 7. Then we have hexadecimal, my favorite actually. Hexadecimal is relatively easy. Hex means 16. So guess what? We now have that 4th bit added to our counting. So let me just tap this there. Thank you. Hex. Basically, we're from 0 all the way to 16. How do we know this? How can we represent this in something that we can easily understand? Well, 0, it's 0, 0, 0, 0. You would have 1, which is 0, 0, 0, 1. And what's the max number that you can get in 4 bits? Well, max number would have 4 ones. And what is this? Uh, I'm also going to teach you how to convert from bits to actual decimal, which is what I've been doing. So right here, the first ones is like 2 to the 0th term, 2 to the 1th term, 2 to the 2nd term, 2 to the 3rd. You're basically starting from 0, counting forwards as you increase in the 1th term. Like how we talk about the number system, like we increase in a 10th. So like you have, like, let's say this is decimal, which is normal how we count. This is the ones. term. This is the tens term. And then if you added another one, that would be the hundreds term. Well, it's like the same thing, right? So if you had to convert this into normal, like human speech, you would say this is just 1 times 0. And then the second term is just 1 times 10. And then the last term is just 100 times 1. So you see how I get that from there? This is just that number representation, right? And then the 0 also comes from above. But we're doing the same thing from binary. So I'm just gonna stress this again and go over it one last time, since you have this as a basis of understanding now. So we have 1, 1, 1, 1. Okay, let's take it. Binary can either be 0 or 1. So we only have a base of 2 to work off of. So let's start. Well, we know that this is the first term. So it's going to be 2 to the 0. We have the second term, which is 2 to the 1. And then we go forward. The third term, 2 to the 3. Fourth, 2 to the 4. And then we would add these together. I'm missing 2. 2, this is 3. And then we add that together. Well, you can see as we add it, 2 to the 0 is 1. 2 to the 1 is just 2. 2 to the 2 is 4. And 2 to the 3 is 8. So it's going to be 8 plus 4, 12, plus 2. This is 14? What the fuck? Is it 14? Oh my god. Yeah, it's 14 plus 1. That's 15. So we call it hexadecimal, but it is still just 2 or 0 to 15. I'm just gonna check just in case if I got it right. Yeah, but this is the tricky part that I forgot to mention. We have everything from 0 to 15, but in hexadecimal, we kind of introduce letters into it. Let me just grab one page. So if I had to type out the whole hexadecimal number system, it would be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, and then F. Now, why do we why whenever we have to introduce another term, we just switch to letters? Well, okay, in a digital system, representing 2 values becomes very space intensive. Like in hexadecimal, in order to represent 10 in order to represent this, like let's say if we wanted to do just a direct conversion, well, this would be 0, 0, 0, 0, and the 1 would be 0, 0, 0, 1. So altogether, it would be 0, 0, 0, 1, 0, 0, 0, 0, which is a lot more than just having A, which represents, A represents, it would be 10, which is 1, 1, 0, 0, right? Because this is just going to go convert this back just for practice. This is 1's term, second term, third term. So it's 2 to the 3 plus 2 to the 2, which is basically 8 plus 4. Wait, I'm doing this wrong. Give me 2 seconds. It's 8 plus 2, which makes 10. So this is now a 0. This is a 1. It's always good to check. This is 1's. So it's 8 plus now 2, which makes 10, right? This is much less memory intensive than having all of this. Okay. So this is not really important, but I'll give you some practice just so you have like a firm understanding. The only questions that you could possibly have are probably in the form of this. You have uh you have let's give me some bits. 1 0 1 1 0. Sure. You have that in binary. Convert to hexadecimal. And then convert to octal. Sure. Convert to decimal. Is this similar to what you've been taught? Table? Or anybody? Have you been taught conversion at all? Okay, good. Eventually. Fair enough. So let's just see where in the slides we're at. Yeah, this basically shows you how you would convert. It's much simpler with practice, and you're gonna have a shit ton of practice as you go forward. Okay, so then they talked about the systems. Okay, we're already 35 slides past, probably more. Okay, now they're talking about conversion on slide 38, but I'll just show you the quick and easy way. Okay, when you have binary, the easiest, like, okay, some people convert to hexadecimal right away. Some people convert to octal. Some people convert to decimal. Doesn't really matter with binary. To be honest, decimal is really nice. So we're gonna do that first. So let's convert to decimal. So decimal, the same thing. I'm gonna use a different color. We're gonna count each term starting from the right all the way to the left. 0, 1, 2, 3, 4. Okay, so we have 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3, and then 2 to the 4. And then we see here, well, since this is a 0 right there, we have 2 to the 0 times 0. And then since this is a 1, we have 2 to the 1 times 1. Since this is a 0, we have 2 to the 2 times 0 plus this is, or wait, sorry, messed up a little bit. This is a 1, so this is times 1 plus that's a 0, so we're timesing by a 0 plus, and then the last term is the 1 multiplied by 1. You see how we split it by this term plus addition, second term plus addition, third term plus addition, and then the last term plus addition. This is the usual way we do it. You can just go right ahead if you're very confident in binary conversion and just pick out all the ones term and write it simply as this: 2 to the 4 plus 2 to the 2 plus 2 to the 1. It's much cleaner, but this is essentially what we're doing broken down. I'll also use some red just so I can stress the terms, make sure that they look different. So we get them from here. So that's the first 0. Then we have the 1, the 0, and the 1. But essentially, we're just doing this calculation because the zeros cancel out. 2 to the 4, that's 16, plus 2 to the 2, which is 4, plus 2 to the 1, which is 2. This would be 2 plus 4, that's 6. 6 plus 16, which is 24. No, 22. 22. And do I check this really quickly, or am I confident? I think I'm confident. That's 22. Okay, so now in decimal, we have 22. You may ask, why do you have the 2 here? Why do you have the 10 next to the bracket? That's just to denote which system that we're using. It's not really important. Please write it though on your exam because you will lose marks. So it is important. but like it's not really necessary for your homework. It's good practice. So now we can choose between octal and hexadecimal. Either one is really simple, okay? And it's very quick. So I'm gonna just do some octal first because it's just the next level. So octal, okay, you know how we have octal, which is from 0, 1, 2, all the way to 7? And everything is represented in 3 bits. Look at how fast the conversion is. How do we represent 2 in 3 bits? Well, 2 in 3 bits is just 0, 1, 0. So 22 is literally 0, 1, 0, 0, 1, 0. That's it. Okay. Now, is hexadecimal different or is it the same? Well, good news. It's the same. We have hexadecimal, which is from 0 all the way to 9. Then we have A all the way to F. How do we represent 22 but in hexadecimal? Well, hexadecimal is 4 bits now. Does it really change? Not really. Hex. How do we represent 2 in 4 bits? Well, we just add an extra 0 basically. So it's 0, 1, 0, 0. And that's it. 0, 0, 1, 0, 0, 0, 1, 0. And that is now in hexadecimal. That's it. This question is usually worth 4 marks, maybe 6 marks on your first midterm. And it's that simple. Any questions? Perfect. Now let's try going from octal to whatever and hexadecimal to whatever, because it might get harder, it might get easier, who knows? Okay, so that was the decimal to the rest of the systems. Now let's try octal. And we're gonna do octal to decimal to hex and to binary. Okay, I want you to give me some ugly numbers. Start with like just spam me with 1 and 0s. Hable if you want. Or whoever is watching, listening. Are you, did you send me some nasty? Oh, okay. You know what? That's not even that bad. That's not even that bad. Okay. So let me just quickly memorize it. Uh, okay. I might need bigger space. Okay, let me just everybody can see our DMs, by the way. No, you're good. 0, 1, 0, 1, 0, 0, 0, 1, and I'm just gonna add the last thing over. Oh my god, this is gonna be ugly to do in decimal, but you set us up, okay? Oh my god. Okay, so this is our ugly number in octal. And now we have to convert it to, let's just convert it to decimal. Why not? So the easiest way to convert it to decimal is, well, you know that octal is represented in 3 bits. We're leveraging that concept to our advantage. That's why I stressed it in the beginning, because low key, like this is the most important concept. Octal, 3 bits. Hexadecimal, 4 bits. Look at how easy it's going to be. We start from the very end and we count 3 bits. Then we keep going. Count each term of 3 bits. And you see how there's stuff at the end that doesn't really fit the 3? That's okay. That's perfectly fine. If you assume that there's a 0 at the end of any like, or zeros from all the way down, it's like you can write as many zeros as the cows come home saying in decimal. Like, let's say this is just a regular 10. If you write zeros here, 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 they don't matter. They don't really affect it. It's still a 10. And that applies the same with binary. That applies the same with hexadecimal and octal. We can leave zeros there. They don't affect it. So we're just going to use that to add an extra 0 to make our third pair. Okay. So basically, we know that octal goes from 0 to 7. And let's see. Well, what is this in terms of binary? This is 0, 1, 1. Well, we know it's, I'm just going to do the first one stretched out and then just speed run the rest. So this is 0, so 2 to the 0, but that's 0, so we don't need it. This is 2 to the 1 plus 2 to the 2, which is 2 to the 1 is 1, 2 to the 2 is 2, so that's 3. So we know this term is 3. And then we do the next. So we have this, which is 0, 1, 0. We know that's 2. We have the next one. This is 1, 0, 0 from there. That is 4. This one, this is 2. That's 4. What's this? This is 3. That's 2. That's it. Done. Okay. Any questions? I kind of went fast. It's really easy. Yeah. So, but the thing is, look, now we have decimal. We can work with the decimal to convert to binary. You know what I mean? All we have to do is divide by 2, and then we get the binary from the decimal. But let's say we wanted to convert to hex now. Okay. Well, hex you can just divide. Okay. How I would do this is now we have octal and we have the decimal number to work with. I would use the decimal number to find the binary, which then I would use to find the hexadecimal. And we already covered binary to hexadecimal conversion in the previous question. But let's just reaffirm it. Okay. This is a long ass number to convert to binary. I'm kind of scared. Low-key, this is gonna be a lot of ones and zeros. So maybe I might just I'm not gonna use an online compiler. Okay. Oh my god. That's a long ass number. uh I said for it to be complicated. Loki, he's gonna give you like this many terms most likely to convert. So I'm just gonna, you know, just use the first 3. So now we have a number that's 2, 3, 4, okay? And then we're gonna convert to binary, and then we're gonna convert to hex. But I just, the long example was good to show you like the strength of converting from octal to decimal. And if you look at octal too, like you wouldn't really see like. Never mind. I'll just continue with this. Okay. So, what's 2 to the power of 7? Is it 128? There are some key things that we need to know. You can just easily divide this, or you can just memorize like 3 things. 2 to the power of 7 is 128. 2 to the power of 6 is 64, right? Right? Yes. Yeah? Okay. Oh my God. I knew this. I had to memorize this for computer architecture. So we know that 134, well, you can break this down to 128 plus 64 plus an x term. 128 plus 64, that is 170. No, that's 182. Okay, 182 minus 234. We have, it's gonna be 2. Oh my god, that's not gonna be 2 that's gonna be 1. Why 7 and 6? Okay. Honestly, there's nothing really specific about it, but when you get numbers up to the 100th term, you won't really reach 2 to the 8. So I haven't even memorized it, so I'm gonna actually just look up 2 to the power of 8. So that's 256. See, like this number would not reach 256. You know what I mean? Because it's below that point. Yeah, exactly. We're picking a number to get close to it, but not surpass it. So 2 to the 7 is a golden spot. 2 to the 6 is also pretty good. 2 to the 8, you would really use it for numbers that are like, as I mentioned, greater than 256. But most likely the professor won't give you these disgusting numbers. Like he'll probably stick to the 100s, right? Like you might get 157 or 94 or something like that. Because I will like explain how we do the division as well. But let's say you had this number 234 and you wanted to do the two's division. Okay? We're gonna divide it by 2. What do we get? Well, we get 2. That's a disgusting number. 5. So this is 1 7. This is 1 1 1 7. Okay. What do we multiply? Like, you know what I mean? Like we have 1 1. Okay, let me just do this properly. Uh, divided by 2. This is 1 1 7. 1 1 7. Okay, and then you subtract, right? 2 3 4. 1 1 7. Wait, give me a second. Give me a second. I kind of forgot how to do the division way. Uh, yeah, okay. I'll figure this out while you come back. Let me just quickly find. Oh, no, okay. Well, how the you're gonna divide it by 2. Okay, you divide this by 2, you get 1 1 7. Yeah, I usually just do straight conversion. I kind of forgot how to do it like the division way. Okay. Oh, so now this is 0. Okay. Yeah, yeah, yeah. No, no, no. I honestly, I think I understand now. Okay. I got you. I got you. So now we do this. We divide 1 1 7 by 2. And that would be 1 1 6. So now we have a 1. Well, it wouldn't be 1 1 6. It would be okay. You drop the 1, take off the 1, and then you have 116. You would have to divide that by 2, which would be 58, right? And then 58 times 2. Okay, let me just re-explain this. So you'd have to divide 1 1 7 by 2, which would be 58, which is the nearest term. 58 times 2, which is 1 1 6. 1 1 7. And then you would have to subtract that. That's 1. And then you'd have to divide 1 1 6 with 2. This is just 1 1. That's just sorry, my bad. 50. Okay, that's just 56. Okay, let me rewrite this. I understand now. Thank you so much though. Okay. So we have 132. We're gonna divide that by 2. This would be 230, 30. Okay, this would be 1 1 7. We have 1 1 7 times by 2. This is gonna be well, it's 234. So that is, if we do the subtraction, that's 0. No, no problem. I finally figured it out, I think. So now we have 1 1 17. We're gonna divide that by 2. That's going to be 50. Did I say 50? Okay, we're going to divide this by 2. This is not a even number, so we're just going to subtract 1. So now we're going to divide it 1/16 by 2, which is going to be 58. 58 times 2, that's 116. So we have a remainder when we subtract, which is 1, and then you would continue going. You have 58. 58 divided by 2. This is an even number, so you can just get 58. That's 0. What times 2 is equal to 58? That's going to be 4, 5, 5, 20. Would it be 20, 26? Oh, 29. Okay, maybe I suck at math. 29. Okay, 29 divided by 2, that is even. It is 29. Yeah, it's even. Wait, 9 is not even. Never mind. Sorry. 28. Well, 28, 20. Yeah. So this is going to be 1. Then you have 2. 2 times what is equal to 28? That's going to be 14. Thank you. I am slow with math when it's this late. Now this is also even. So we have, oh, fuck. Sorry, my system does that sometimes. This is, put a 0 down. Yeah, basically, yes. So we have 2 here. Oh yeah, the 2's. Oh no. I'll explain the division like on the other side of the decimal. But yes, you're correct. But like there's an easier way. Like that I know. Because it's very simple. This you're dividing, so that's just 1. So now we have, this is 2, 2 to the 2. This is just 1. So we have 0 and then we have 1. So basically we have this long list of remainders. And we have to take this list going from, where is my mouse? Okay. Going from this side up. So basically our number is now 101101010. This is equal to 250. Did we say 258? 234. Sorry. 234. And what I mentioned above about 128 and then the 64, so like 2 to the 7 and 2 to the 6. If you counted here, this is 0, 1, 2, 3, 4, 5, 6, 7, 8. Wait, did I do this right? 0, 1. Okay. Never mind. Opposite way. That's a good check, actually. Let me just do this and write this sure in green. This is, so we start off from up to down, but we copy this at the right. So this is 1 0 1 1 0 1 0 1, right? 1 0 1 1 0 1 0 1. Okay. And then if we had to do a recount, so we could easily convert this back to decimal to check our answer. Let's go here. So now we're at, this is the zeroth term, 1, 2, 3, 4, 5, 6, 7. 234. Wait a minute. This is 128 plus 64 plus all I would need is 16. Or not even that. I could just go 32 plus 4 plus 16. That's too much, so plus 8. And then plus 2. Just checking in like the binary conversion. So the correct answer is, if I convert that, it would be 2 to the 7 plus 2 to the 6 plus 2 to the 5 plus 2 to the 3 plus 2 to the 1. That is the correct answer, which would basically be 0, 1, 0, 0, 1, 0, 1, 1, 0, 1, 1, 1. Did I get that? I would have gotten it. Maybe I messed up. Anyways, it'll probably be pretty simple. I probably messed up somewhere in the division. Somebody can call me out for that. But like I said, an easier way to convert is if you just know like this as a base. The rest of them before 2 to the power of 6 are pretty easy because it's just you just divide 64 by 2, then you get 32, and then you do the next 32 divided by 2, 16, and then so forth. And then you just add till you reach the number. Yeah, I'll probably go back and figure out what I did wrong. I just haven't used the division method in a long time. Let me see if I can spot it quickly. I should probably get a calculator to check my shit. Let's just do the things that I wasn't confident on. 2 divided by 2. Okay, that's 116 divided by 2. That's 58. Okay, I got that correct. 58 divided by 2. That's 29. That is correct. That's 14. That's correct. 7. That's correct. Oh, 6. 2 times. So this is 3. No, that's correct. Okay. Yo, can anybody spot what I did wrong? 3 is here. 2. Okay, that's 2. That's 1. Then we have 2 times what? Oh, this is 1. Okay. 2, and then that's 0. Okay, it's 1. Here, let me take this. I'm just gonna take this singular part and bring it out right here. So we have 7, 6. We dropped it down. We know that's 1. So we're dividing by 2. 2 times what is equal to 6? 3. 2 divided by 3. We have 2. We drop that out. That's 1. 2 times what is equal to 2? 1. 2 divided by 1, it's just 1. So we drop the 1. That's why we end up with 1's right here. So instead of a 0, it's actually just a 1. So yeah, it's 3 1's. So if you wanted to copy it onto your page, doing this for the last time, hopefully, because I know this is correct now, you're going to go from the start to the very end. So basically, you're going to start here, go up all the way to the very end, and copy it from this side. Wait, where is it? From this side downwards. Okay, let me do this in red. So you're starting from here going all the way up. And then on your actual like answer sheet, you're going this way. So we have 1, 1, 1, 0, 1, 0, 1, 0. This 0 matters. The 0 on this end really matter, okay? Like if you have an extra 0, you have to add that extra 0 to that end. Okay, perfect. And is that what we got down here? Yes. So if you wanted to check your answer, you can convert this to decimal. And yeah, and if you wanted to do like the conversion the quick way, like I said before, all you have to do is kind of memorize 2 to the 7, 2 to the 6, and then you just have to find what adds up to the actual number. So 234. In this case, I calculated it on my Chrome tab, but it was 32, or wait, yeah, it was 32 plus, I think, 8 plus 4, right? 32 plus 8 plus 4. Let me check the actual number. Yeah, 32 plus 8 plus 4. 32 plus 8 plus 2, not 4. Okay. And that was pretty much it. So that's all for conversion. It gets easier with practice. That's like a guarantee. Okay, let's see what else was covered. Binary to octal is pretty easy. So once you have binary, let's say you wanted to convert this to hexadecimal, and I did this previously, but I'll do it again just to stress how easy it is. Well, you have 4, or not even that. Like, if you have binary and you want to convert binary to hexadecimal, like let's say you had, okay, because initially, what did we have? Oh no, we already had decimal. Okay, we could have done this right away. Well, let's say you wanted to convert this to hex. Well, you have 0, 1, 0, 1. Since hex, we use 4 bits to represent it. So this in hexadecimal is, this is 2 and this is 8. 2 plus 8 is 10, right? But in hexadecimal, we have no 10. It's represented by A. So this is A, and then we count the next 4. This is 8 plus 4 plus 2. So that's 14. 14. On my sheet, I usually like writing this at 9 A B C D E F. Okay? Because that keeps me kind of grounded on this weird alphabet. So you know that the max number is 1111, and that's 15. That's F. So we know that since we're missing 1 off of that, because we have 14, this is going to be E. So actually, this is EA in hex. EA sports. It's in the name. Yeah, exactly. That callback. But yeah, okay. I'll just reiterate some key things to know. New page. Don't discard. Just give me a new page. Cancel. Okay. Key things. 2 to the 7, 128. 2 to the 6, 64. Hex is 4 bits. And it's from 0 to 9, A, B, C, D, E, F, where F is 1111, which is equal to 15. And then also octal, which is 3 bits, which is 0 to 7, where 7 is just 1111, or no, 111. And then the conversion is pretty simple. You just manipulate the actual bits at play. Okay, this is just going to be a straight list of just key things. I'm going to do a quick search of the rest of the slide and see what else the professor has covered, or if he hasn't covered it. This is just conversion. Okay, then he does binary operations. Binary operations are really simple. Don't even bother learning multiplication. It is never tested on. But I will give you some nice addition. So I'm gonna have like blah blah blah. Cool. And then we have 0, 1, 1, 1, 0, 1, 0, 1, 1, 1, 1, 0. Okay. When you add binary together, a 1 plus a 0 is a 1. A 1 and a 1, well, whenever you have a 1 and 1, you're going to have to take this as a carry. So we right here, cross this out. This is, oh wait, wrong spot. Cross this out, write the 1 up there, leave this as 0. Okay, now we have a 1 up here and a 1 down there, which is just going to be a carry again. Cross this out, we carry the 1. So whenever you have 1 plus 1 plus 1 in binary, this is going to be a drop plus a carry. So basically what this looks like is you have an example right here. That's 3 ones added together. You're going to put a 1 down and then also carry a 1 to the next side. Okay, you see here, this is a carry. So we put 1 here, put a 0. That's a carry. 1 here, 0. This is another one where you have 3 ones. When you have 3 ones, you put 1 down and you also carry a 1. This is a carry state. This is carry. This is carry. And this is carry. Okay, but what happens to the 1 at the very end? Well, you just add it to the very end. This is what we call overflow. Overflow essentially means that you have a number that does not fit in your registers and it's overflowing. So when you're, let's say you have a maximum of 3 bits. Okay, what is the range of this number if it's not signed? We'll talk about signed later. What is the range of 3 bits? Well, you can go from 0 all the way to 7. What would I tell you if I added 111 to 111? Well, in decimal, this is 7 plus 7, which is 14. Does 14 exist in this limit? No. So you would have an overflow. So 111 would actually just be 0, 1, 1, 1. You would only really see this is 2 plus 4. You'd only really see 6. This one is missing. Okay, this is what we call overflow. Very important concept to get around. This is just the easiest explanation. If you don't understand, just try to think, okay, what's a maximum? Yeah, try to, it doesn't disappear. It's there. You still have to consider it when you're doing calculations. You still have to write it on the page that it's overflow. Sometimes it does disappear, but sometimes we use overflow as a signal. It's really important in your second year course. And I go through overflow actually in one of my videos, like more in depth. Don't search for them because like you will get confused with the other stuff covered in those videos. But don't think of it as it just disappears. Think of it as like, okay, this is a sign that this calculation will not work. And it's the same thing. Yeah, outside the scope. Exactly. Exactly. So like, well, look, if the scope was 4 bits, this would be 2 plus 4 plus 8. That's 14, right? But since the scope is just 3, this is just 6. You know, like it causes errors, and it's something to just recognize. I think I covered binary addition pretty good. I covered overflow, which is really good. Yeah, it's the carryover. What else? Multiplication, I won't lie. I think I walked out halfway of the lecture during my multiplication lecture. I didn't learn it. You don't have to know it. Um, yeah, so I cannot answer that to be honest, but it's covered in the notes. Subtraction, okay. Subtraction is kind of interesting and you could just use some conversion rules and be like, okay, now I know the range. But in larger functions, let's say he gives you, let's say he even asks for the formula. He's like, yo, give me this formula for n numbers. Uh, then you might run into some stuff. So let's just keep the formula as how you said, 2 to the minus 2 to the power of n, then it's 2 to the n minus 1 as the range. Minus 1. Yeah, because we had 0, 1, 1, which is the highest positive, which is just 3. So that's 2 to the 2 power of 2, which is 4 minus 1. Yeah. So that is just going to be our formula for now. I will change it maybe eventually later. But let's go to subtraction. So in subtraction, we're going to discard any signed bits. Okay, that was just for fun. Now we're just going to subtract two binary numbers as we see it. Okay. In subtraction, it's going to be simple. We're just going to take each term by term. And then if you have a 1, subtract a 1, it's just going to be 0. 1, you just drop it down. So you just drop it down. And then that's pretty much it. There's no really carry because you can always subtract with ones. So this would be 0. We just drop the 1 here, drop the 1 here, here. Or yeah, I'm pretty sure you just drop the 1. You might need to actually carry and put the 1 here and then carry, put the 1 there. But I think that's just in normal English. Let me check what they get. Because I might be just thinking about. Yeah, they just dropped the 1. Thank God. Okay. Yeah, this is correct. Let's say you had subtraction. And you can actually like check if you convert this to binary, you can see that this number subtracted by that number is this number. Like these numbers work throughout the subsystem. Like if you convert, it's still the same subtraction. Uh, this is actually a really good way to test your questions. Like see if you got it right on the test. Just do a quick, simple conversion to decimal and subtract. And you know what? If you really want to cheat the system, convert it to decimal, subtract, and convert your solution to binary. Okay, and pretend that you did like some cool subtraction on the sheet of paper. That has been really helpful. Now let's say this was sign bits. Okay, let's try this with sign bits. Let's say we wanted to subtract two sign bits. We have 0, 1, 0, 0, 1, 1, and then we have 1, 0, 1, 1, 0, 1. And we're going to subtract them. Okay, for sign bits, this is a negative number. And we want to do some conversion in order to write it as a positive so we can actually subtract. So we know that this is negative. This is negative, and we're going to take the 2's complement. So let's just bring this down here. This is negative, so this is negative, and we take the 1's complement and we add 1. Or another trick for taking the 2's complement is that you go up the number until you find the first 1. And that's a 1. And you keep it the same. And then for the rest, you take 1's complement. So this is going to be a 1, 0, 0, 1, 0. I'm going to go through this trick once more with a complicated like another number so you actually understand it. let me get some red out, or like another orange, sure. Let's say you had a number like this. Okay. And you wanted to take the 2's complement very fast. Well, you start on the right side and you track until you see the first one, and then you just copy that over. Right? And then you do 1's complement for the rest. So this is same. This is 1's. So basically, you copy this same, and then you take the 1's complement for everything after the first one, which would be 1, 0, 0, 1, 0. And that is the 2's complement. For this situation, we just had the first initial 1, so everything else was a 1's complement. Okay, now we're going to subtract these 2 values. Yeah, now we're going to subtract. So to subtract, we just add. That's pretty much it. So let me just put this here. So to subtract these, it's 1, 0, 0, 0, 1, 1, 1, 0, 1, 1, 0, 1. But we converted it, so now we have 1, 1, 0, 0, 1, 0. Okay. And now we subtract. This is, oh, well, we add, because once we take the 2's complement, now we're adding these two numbers together. This is 0. We have a carry. 1. We also have a carry. That's 1, 0, 0, 1. Okay. Now look at what happened with our number. We took the 2's complement. Okay, which converted this negative number to a positive. Well, it didn't really convert the negative number to a positive. We just wrote it as a positive because it's still negative. But we made it in terms of we can do addition and subtraction to it. And the solution that we got was negative. Right? Because right here is a negative number. Because it starts with a 1. So what do we do, really? We did subtraction. But it's utilizing like our previously stated concepts. So let me just write this. Actually, can I just take a screenshot of this and move it? Perfect. Let me just quickly put this down. Okay. Here, let me just quickly take a screenshot of this, move it down so we can work with a fresh page. Okay. Plus that. Sorry, it might be a little laggy. Okay. So right here, we have a negative number. Now, we're going to see what the solution is. So we're going to try to convert this back using 2's complement. Okay, how do we do that? Well, we're going to use the same trick that we learned before. The first, we're going to track it up to the first 1. So this is 0, 1. Okay, we got our first 1. Now the rest, we're going to take 1's complement. So this is 0, 1, 1, 0. So we got negative 0, 1, 1, 0, 1, 0 as our answer. Why? Why did we get a negative value for our answer for subtraction? Well, let's convert. Let's convert these numbers back to their decimal representation. and see if this makes sense. I'm hoping it makes sense. uh, right here. What is this number in decimal? Well, we have 1. So I'm just gonna rewrite it here so I can quickly convert it. Actually, I'll just rewrite it here so I can quickly convert it. We have negative 0, 1, 0, 0, 1, 1. We're gonna quickly convert that to decimal. What do we do? This is 1 plus 2 plus, this is the third term, fourth term, fifth term. So that's 16. Yeah, which is negative 8, negative 19. Okay. And what was the number above it? This number is 0, 1, 0, 0, 1, 1. Wait. This is the same value. Oh. Hmm. We're doing subtraction, okay. Subtraction is just 2 complements and then addition. No. Usually only on the negative number. Actually. Wait. Okay. I actually don't think we had to take the 2's complement for this one. It's just weird. Okay. Let me give a smaller example actually and just clear it up. So this is subtraction. Let's say you had like this. You have A minus B. Okay. Then you have minus A minus B. Then you have A minus B, or minus A plus a negative B. Okay. And let's keep this very simple. Let's say A was, they might give you binary numbers, they might give you decimal numbers. Let's say A was 16 or 8. Let's say B is 11. Okay. 8 is going to be 0, 1, 1, 0, 0. 11 is going to be 1, 1. Wait, let's not use 11. Let's use something with 3 bits. Actually, does it matter? No, but I'm going to use, what should I use? 52? No, wait, bruh. Actually, no, since this is 1, 0, 0, 0. Okay, this works. 11 is going to be, it's going to be 1, 0, 1, 1. Okay, there. Now we converted A and B to binary representations. Let's say they wanted you to do A minus B. Well, you're going to just do 0, minus 1, 0, 1, 1. Okay, subtraction in this case is 2's complement, and then you use addition. Okay, so when they have like negative A minus B, you're gonna take the 2's complement, and then you're gonna of B, and then you're gonna do addition. So in this case, what's the 2's complement of B? B's 2's. Well, B is equal to 1, 0, 1, 1. Taking the 2's complement, so it's negative B. Negative B is now 1, 0, 1, 0. And we write this as negative 0, 1, 0, 1. Okay? So when you're doing A minus B, in this case, you have 1, 0, 0, 0 minus 1, minus 0, 1, 0, 1. And you're actually doing addition. So this is 1, 0, 1, 1. You see this value? You have a negative number. Why do you have a negative number? Does this make sense? Well, you're doing 11 minus 8, or 8 minus 11. That will give you a negative number. How do we convert it into something we understand? Well, we have a negative. Whenever you see that we have a negative, we're going to take 2's complement to convert it back to a positive, like a positive value that we can understand. So we have a negative. We're going to convert this to positive using 2's complement. We have 1, 1, 0, 1. Taking 2's complement, the first one stays the same. The rest is just 1's complement, which is 1, 0, 0. What is this value in decimal? So this is now positive. Well, this is negative, right? But if this inside is something that we can actually interpret. What is this in decimal? Well, this is 3. So we got negative 3. And if you check your answer before, 8 minus 11, that's negative 3. So we did the right subtraction and order. Oh shit. Thank you. Tired. See, that's negative 3. Okay, now let's do negative a minus b. Well, it's going to be the same thing. We have b. So now we're going to do the a's 2's complement. Okay? What's a 2's complement of a? A is 1, 0, 0, 0. So we have a, which is now 1, 0, 0, 0. Taking the 2's complement, nothing changes until the first one, and then you take one's, okay. Nothing changes until the first one, and then you take one's complement. This is actually a really interesting example, because if nothing changes until the first one, you have 1, 0, 0, 0 as a 2's complement. But does that make sense? Not really. Can I make it make sense? Sure. Let's just see what we would do. What happens if you take one's complement and you add 1? Well, because this is basically 2's complement. Okay, let's take 1's complement of a. It's going to be 0, 1, 1, 1. Let's add 1. Well, if you add 1 to that, you're going to have a carry, a carry, a carry, and then 1. So 8 is the ultimate, 8 is the ultimate fucking number, because it's 1's complement. I think so. Yeah, I think it's because it's on the edge of the scope, and it just is struggling to be converted. Yeah, so I'm gonna change A to be I'm gonna change A to be 0, 1, just for this example, just so I can show you guys. But since it's because it's on the edge of the interval, it won't work out. But let's just pretend A is now valued as 4. Taking it 2's complement would be 1, 1, 0, 0. Okay, so now we're gonna do negative A minus B. So we take the negative A, and we have minus negative B. Where is B? B is 0, 1, 0, 1. But that's a 2's complement. What is A in general? A in general is, or B in general, sorry. It's 1, 0, 1, 1. Do you think we have to take the 2's complement or no? Well, we already took the 2's complement of A. I have to take the 2's complement of B. Let me quickly do that. Oh, wait. Wait a minute. I think I got confused because A is already negative in this state. Or, I mean, A is positive, then we turn it to a negative. No, never mind. We're still good. Okay, thank God. B was initially negative. I'm gonna add another dot or another zero to these just so it makes sense, okay? Yeah, maybe I should have done that before. Because if you're working in signed states, everything's in signed states. Yeah. So I'm gonna it doesn't affect the calculation above because that's correct. But I'm gonna keep A to be 8. So A is 8, B is 11. But we're working in 5 bits. So 8 is now 0, 1, 0, 0, 0. We're taking 2's complement of this, which is now 1, 1, 0, 0, 0. For B, we're gonna take B's and we're gonna do the 2's complement. Okay, B is 11. What did we say 11 was? 11 is 1, 0, 1, 1, right? Now we're just adding an extra 0 because we're working in the 5 bits. We're gonna take the 2's complement, which is gonna be 1, 0, 1, 0, 1. Okay, now we have negative A minus a minus B. How do we do this? Well, we take the negative values, 1, 1, 0, 0, 0, and then we have negative B, which is 1, 0, 1, 0, 1. And do we add or do we subtract? Well, we add. This is 1, 0, 1, 1, 0, and then we have a carry. Now the value that results is positive. How is it positive if you're adding two negative numbers? You know what I mean? Well, this is just because of overflow. If you took this number as a whole, it would be negative. If you took this number as a whole, what is minus 8 minus 11? Minus 8 minus 11, that's minus 19. If you had to convert this, so this is negative. Let's just take the 2's complement just to see. So this would be 1, 1, 0, 0, 1, 0. And this would be a negative number. What would be this value? It's 1 plus 2. This is 3 plus 16. So this is negative 19. But since this does not fit in the range, we have overflow. Therefore, the value is positive at its solution. So that's like another thing to be wary of. When you add two negatives, you won't always get a negative value. Sometimes you get a positive, but that's usually because of overflow. Okay. Then the last thing was just how did you deal with the overflow? That's good. Overflow, the thing is, it's hard. Let's say the question asked you to write the answer at the end of the day. You would just include the overflow. Because if you don't, then it's wrong. Let's say the question asks you, like, okay, what is the answer? Or like the professor tells you something different. He's like, okay, ignore overflow. What is the answer? Well, for this, if you ignore overflow, the answer is we're going to convert 0, 1, 1, 0, 1 to decimal. That's 1 plus, this is 4 plus 8, so that's 13. So you honestly, if you state clearly on your page that including overflow, the value is negative 19, excluding overflow, the value is 13, you will get full marks. If you state that the value is 13, you will probably also get full marks because you can just point at it and say overflow and ignore it. But like really, like this concept is very important in computer architecture because overflow matters a lot. Uh, so getting like comfortable with these types of calculations is very useful. I have messed up previously, like with the range stuff, but range you can just rememorize it. Most of the calculations you kind of have to know. And there's always good ways to check. So for just like in general, like this stuff, uh honestly, just if you're gonna review subtraction, addition using signed numbers, let me just look at signed. Do these examples, because that essentially is what's gonna be on your exam. You're gonna have an A and a B. They're probably gonna be in decimal. They're probably gonna you have to convert it to binary, do the addition, do the subtraction, and knowing whether something is negative or not, and what you should do if you get a negative answer at the end of the day, what you should do if you get overflow is going to be really important. Yeah, that's pretty much it. I'm going to check through the slides one last time. Okay, 9's complement and 10's complement is not useful at all. I don't even think it was tested on, but a hint is that 9's complement, okay, uh, no, well, not really. 10's complement, you basically have to like okay. You know how the difference between 2's complement and 1's complement? 2's complement is just 1's complement plus 1. It's the same with 9's. So like 9's complement, let's say you have a big decimal number. You can only do 9's complement in decimal. Binary, you just have to convert to decimal and then do it. But let's say you have something like 1, 4, 3, and you want to convert it to 9's. You know what's a good trick? Subtract by 9's. So now this is okay. Let me do this. Let me just erase this so I can actually just quickly cover 9's complement. Yeah. No, you don't even have to do minus. This is just 6, 5, 8. There you go. You got the 9's complement. What's the 10's? Add 1. Crazy. This is now 10's complement. What's the points of complement? This is a perfect question. Exactly. Complements are like in the binary level, complements are very important. Like you use it in hexadecimal to it, but okay. In terms of sign numbers, complements are the conversion of a binary number from negative to positive and vice versa. In terms of 10's and 9's complement, it's just I wouldn't say it's really important. But let's say you had to find the number. Like they give you the 10's complement and they're like, what number is this? I think you could actually just subtract it by 1,000 and get the same number again. Yeah. So that's essentially what's like the main thing because you have 3 digits. This is 0, 1, 2. And altogether it's 3. 1, 2, 3. So you have 3 to the 10 minus 8 to the 57, which would be that number again. But that's honestly, if you just know like the subtraction by 9 rule, like that I did right here, where I just subtracted the number by 9 and then the adding 1 for 10, that's all you need to know. Anything else is pointless. Okay. You asked me what's the difference between doing first complements and second complements. Okay. No, I have to repeat because they can't hear you. Like I realize that. But let's say you have okay. That's a good question. Let's say you wanted to do subtraction, but you're only just taking the ones complement. Let's say you have 0, 1, 0, 0, 0. Okay? And you want to subtract that from, that's already a negative. No, that's a positive. You want to subtract that by 0, 1, 0, 1, 0. Okay? You're just taking, if you take just the ones complement, then it's gonna be 1, 0, 1, 0, 1. This is just a wrong answer. Yeah. Like you just have to take the two's complement. They don't really like one's complement is important to know, but it's only important in terms of two's complement so far. I've never used one's complement. Actually, it might be okay, you might get to like an adder or like a full adder, and then the ones complement is important. Like you know this symbol that you use in circuits? The not. You're basically look, look, this is the not. Okay, I'm gonna blow your mind in like 2 seconds. No, no, no. This is just not. So like let's say you have X and you're feeding it into this line. This would be just X prime or however you write it. So let's say you fed in a 1. On the output, it would be a 0. Let's say you fed in a 0, the output would be 1. This basically just takes the ones complement. Now, if you wanted to get really complicated, which you will be getting into very soon, you would make something called an adder, which basically adds two binary numbers together, right? And I won't cover it this week because I'm basically only doing week 1. That's pretty much it. ASCII code's very easy. You guys just did the same things as me. Basic Boolean operations. Yeah, it's discrete math. Logic gates are very fun. Maybe I cover logic gates just in case. So we did not. We're gonna do and. Let's say you have x, y, and your output is something like f. Let's say x and y. Let me just rewrite that neatly. If x and y is 0, 0, 0, 1, 1, 0, 1, 1. What would f be? F would be 0, 0, 0, 1. It's only activated when both x and y are activated. Now let's say we have an OR gate. Again, it's f. Fed into it is x and y. You have x, you have y. You have f. You have 0, 0, 0, 1, 1, 0, 1, 1, 0, 1, 1, 1. F is activated when either F or X or Y is activated. Let's say you have an X OR gate. Exactly. One is activated, but not both. So for this, you have X, Y, you have F, 0, 0, 0, 1, 1, 1, 1, 0. Oh my God. If anybody is in an upper year, you know why I made that mistake. Everybody else will think that I'm just dyslexic. 0, 0. This is just gonna be 0, 1, 1, 0. Okay. What else? Did you guys cover NOR gates? Okay, so this is an OR gate. But since we have a bubble, think of bubbles as negation, which basically takes the opposite of what you would think. This is F. We have here X and Y. We have F here. This is 0, 0, 0, 1, 1, 0, 1, 1. Okay, for an OR gate, you take the opposite of what you think. So this would usually output 0, but instead it's going to output 1. This would output 1, it's going to be output 0, 0, 0. Don't you see some similarities between this NOR gate and the AND gate? If you do, you are correct. This is equivalent to this. Okay, does this equivalence work the same with the NAND gate? Let's see, you have X and Y, and you have F. 0, 0, 0, 1, 1, 0, 1, 1. Okay, what is the output? So in usual case, this would output 0 in an AND circuit. But since we have the negation, it's the opposite. So now we output a 1. Then this would be also 1, 1, and 0. Is this familiar with something that we've already covered? Wait, give me a second. 0, 0. It's supposed to be familiar with one of these. Okay. Usually NAND gates are equivalent to wait. Am I tweaking? Oh, that's not an adder, this is an OR. Okay. Uh that would just be equivalent to an OR. Give me 2 seconds. Let me think about this. Okay, I know this is true. This is gonna be okay. This is 0. This is 1, 1, 1, 1. So that would be 1, 0, 0, 0. It should be the opposite of this, and it is. Okay, there's just no equivalence. Wait, yeah, it's just a moment. Like fuck. Uh, and but yeah, this is just the most important NOR and their equivalent. I know there's like one other equivalency, but I'm not really remembering it. Lovely. NOR. This is just NAND. What else? This is XOR. This is AND. And then that's pretty much it for like the first week of ITI 1100, right? Did logic algebra? Okay. Let me see. NOR and NAND are very important. Let me see if they talk about any equivalents. Okay, they don't. Great. So I'm getting ahead of myself. But that's pretty much it, right? Perfect. Timing outputs is really nice. Okay, I'm just gonna give a full view. It is essentially a simulation of a circuit. Okay, I'm just gonna give a quick preview of everything we covered. Sorry for the little mess up in the middle. I was just trying to remember how to do stuff. It's been a year. Anyways, I'll see you next time. Good luck. Hopefully this helped out. No problem. No problem.